Hi. As part of this week's review videos about sorting, today I'm going to be going over selection sort and insertion sort. They're both pretty similar in how they function. Even I get confused as to the difference between them every now and then, but they are different in some key ways and are pretty useful to know. So we're going to start with selection sort. And the way it works is basically you go through the whole array and you find your smallest element in the array. So you find the minimum item. And we know that minimum item has to go in the first slot if you're sorting it, ascending, obviously. So the smallest thing is guaranteed to have to go to index 0. So we find the smallest one and swap it with whatever's at 0. So that way we know that if you just look at index 0, that subarray of just one item, that's sorted. Obviously, because one array of one item is sorted. But if you repeat this, look for the second smallest item and put it at the second spot, which is index 1. Now the array through 0 and 1 indices is sorted because you got the smallest and then the second smallest. And then you keep doing this, you find the third smallest, put it in index 2, and you keep going on, and you build up your sorted array starting from the left to the right by finding the minimum at each spot. So you find the minimum, then the second minimum, and then the third minimum. And this is all happening in place because we're not using any other data structure or any other storage to go back and come back to this same array. We're just doing swaps within the one array or within the one list, or whatever collection you're using. So this is in place. It's constant memory usage. And this is actually guaranteed to always be O of n squared. There's no best case, there's no worst case. Every case is O of n squared. Because no matter what, when you're searching for the minimum item at any given iteration of your selection sort, you're guaranteed to have to search the entire subarray that you're searching, right? Because the minimum item could be at index 0, but it could be at the very last item. And the same thing with your second minimum, your third minimum. It could be anywhere in that subarray you're searching. So you have to search the whole thing. So that means you first search n items, then you search n minus 1 items, then you search n minus 2 items. And as we know, as we learned in class, the summation of those n plus n minus 1, and so on and so forth, that'll give us an O of n squared runtime. So that's why, given the way this algorithm works and why you have to search your remaining subarray every time, the whole thing, this algorithm is always guaranteed to be O of n squared. There's no way around it. So to sum up, here are the statistics for selection sort. Always n squared, it is in place, and it's not stable, which I'll go over soon. So working through an example of selection sort, because working through an example visually is always easier than just me explaining it in words. So we'll start with this array. And like I said, we're going to build up our sorted part from the left side. So at every iteration, starting from the left, you're going to have I items, if I is your counter. You're going to have I items in your left side, which you consider a separate subarray. You have I items that are in sorted order, and then you have n minus I that you still need to find. Like you still need to search through it for the next minimum every time. So right now I is 0. We have nothing in our sorted subarray, and we have everything in our unsorted subarray to search from. So in our first iteration, we look for the minimum of the entire array, which happens to be the 0, which is at the second last spot. So we'll swap it with the first item. And now that subarray of just one item is completely sorted. And 10 moves to where 0 went. The easiest thing to do, the reason why we're swapping and not inserting or doing anything else, it's just the easiest thing to do. Might as well swap it. And I'll go over swaps versus inserts later. Second iteration, you find the second smallest item, which is this 2. You put it at the second spot, which is index 1. So now we have these 2 items that are sorted. A subarray of 2 that's completely sorted. So we run through it again. 5 is the smallest one. We only need to swap it with the thing that's 1 previous. So that's 13. But again, we wouldn't have known that 5 is the minimum without searching through all of this, right? You can't know it's the minimum until you've cleared every other possible alternative. Further proving what this is the O n squared I talked about earlier. So you find the 5, swap it. Now 13 moves there. Find the next minimum, 8. Poor 13 has to move again. The next minimum is 9. you swap, next minimum is 10, you swap, and by now you see how this works. It's a pretty cool algorithm. 13 doesn't actually have to move. You go through that subarray of 2 items. You find that 13 is the minimum, and then you realize that the index that 13 has to move to is where it's already at. So you're done. And then when you've got 1 item left, maybe you could have a early exit where you just don't even need to check it because it's already in the right spot no matter what. Or you could check it, and either way, it would look like this. So that's selection sort done. It's not a particularly fast algorithm. It's always guaranteed to be O of n squared, and as we've talked about in class, a lot of the best sorting algorithms are O of n log n. So selection sort isn't something you necessarily want to be using in practice. Now going over stability once again, as I mentioned earlier, it wasn't stable, not a stable sort. And what that means is, just as a reminder, basically if you have 2 items that are tied, so let's say in this, it's a array of people objects or employee objects, and you want to sort it by age, but these employee objects also contain other fields that separate them, so they're not exactly the same object. But what you're sorting by is one thing. And basically, a stable sort would make it so when you're done sorting it, if there are ties, the objects will be in the order, the relative order at which they came in. But if it was unstable, they could be in any order. So for instance, in this array, we have both of these objects are of age 27, or item is 27, which you're sorting by, but they have different names. One is Jim and one is Pam. So a stable sort would do this. In the initial array, Jim came before Pam. And so our stable sort would have Jim before Pam when it's done sorted. Like this part would be sorted, all of this would be sorted. But these two, the relative order was Jim and then Pam in the initial array. And that stays the same after your sort. That means it's stable. But if it were unstable, it could look like this, where it's still technically sorted. 27 is not less than 27. They can both be there, it's fine, as long as, this is less than 27, these are greater than 27. But the relative order has changed. Now Pam comes before Jim, which is not how it happened in the initial array. So that's what stability means. So using that, is selection sort stable? Well, and I'm ripping this straight from the section slides, but I thought it was a good example. Consider this array. So the way selection sort works with just swaps, you're swapping anything in the entire array with that first item. So you would go through this. If you want to do this by hand, it's pretty short. You would go through this. You'd find that the minimum is 1. You'd swap 1 with 2a, and you end up with this. And then your algorithm would go, hey, I'm sorting only by 2. You're not sorting by B, C, and A, right? So you wouldn't change things around any further. You would say that 2 is in the right spot, and then the next 2 is in the right spot, and the next 2 is in the right spot. If it was like a composite sort where you were sorting by multiple fields, then maybe you would do something, but that's not the case. You're just sorting by the number, and it just so happens that this object contains other fields. And we're just using the fact that these objects contain other fields to illustrate the process of stability, the property of stability, I mean. So think of just all of these as number 2, but in different order. A stable sort would have all the 2 objects with item 2 in the right order as they came in, but selection sort does not do that because it doesn't guarantee where you're going to swap things to. So you could swap, like in this case, you swap 2a to the very end. And then because even though it's sorted, selection sort would, this does sort it by what you want to sort it by. Selection sort does that properly, but it doesn't guarantee that it's going to be stable. Sort of a long-winded explanation, but essentially just know that selection sort is not stable, and it can be proven by simple examples like this. Now moving on to insertion sort, it's a little bit different than selection sort. Whereas selection sort, you know the next place that your element is going to go, right? It's like in selection sort, at each iteration, you're looking for, hey, what's the item I'm going to put in index 0? Hey, what's the item I'm going to put in index 1? You know that place where that item is going to go, but you don't know which item you're going to put there. The way insertion sort works is you look at an item and you know what the item is, and then you have to shift it around a little bit to find its right place. So if that helps you differentiate between the two of them, that's great, but the example should help do that more. So basically, kind of like in selection sort, we're starting from the left and we're building up a sorted subarray from the left. So you'll say, hey, I'm this many iterations in, this left part, let's say it's of size 3, we have these three items that is sorted. This part is sorted. And the rest of it, n minus 3, these items are not sorted. That's still we have to pull from and still have to sort those. So in that way, insertion sort and selection sort are the same. And we use this property that the first element, if we just consider, that's how insertion sort works. We look at the first item and we say that, hey, that first item is in a subarray of size 1. So that first item is already sorted. And then we look at the next item, and then we incorporate that into the subarray with the first item. So we say, all right, this subarray of length 1 is sorted, and now we have a subarray of a length 2. So if this second item is less than your first item, you shift it to the left. And now, and if it isn't, you keep it where it is. And now those two items make up a sorted subarray of size 2. Similarly, you take the third item next, and if it's less than what's at index 1, the second item, you can move it left. And then if it's less than the first item at index 0, you'd move it left again. So now you have a sorted subarray of size 3. So we're building on the fact that a subarray of size 1 is already sorted, and then we're incorporating just one item and shifting it to the left a few times as need be to further build up a sorted subarray. And we repeat this until that left side is of size n, again, similar to selection sort. And then here are the overall statistics. So its worst case is n squared, and generally is going to be n squared. In practice, we say that insertion sort is an n squared algorithm, but as I'll go over, it's because it's very important, there are some cases where insertion sort is actually on the order of n, which is really fast for a sort. Like selection sort, since we're just doing some swaps, some shifting around, insertion sort is in place. We don't need another data structure to do it. And insertion sort actually is stable as opposed to selection sort. There's a key difference there, and I'll go over that as well after I do an example. Once again, my words alone may not exactly illustrate how insertion sort works, but an example might. So insertion sort, so we just look at the first item, and we say that first item is in its own subarray, and that subarray, since there's only one item, is sorted. And that right part, all those blue items, are in whatever. They're on their own. We're going to pull from that at each step, but we consider them separate. So that first part is sorted, and then we move the subarray by 1. We increase the size of the subarray by 1. So we're incorporating this 8 into our sorted subarray. And now we see that 8, we look to the left. 8 is not greater than 10, so we have to shift it to the left to keep that left side subarray sorted. So once again, we have this black bar, which represents the divide between our sorted and our unsorted parts. We move that 1 to incorporate the 8, and now we have to keep that left part sorted, because right now it's not sorted. And the way we do that is just by some left shifts. So we just left shift the 8 by 1, we move it to the left by 1, because that's all you need to do in this case, since it's pretty small, that subarray. We move it by 1, and now 8 and 10, if you just look at that array containing only 8 and 10, that's sorted. So we're keeping that sorted part going. That's good. So now we increase it by 1, that sorted subarray. We incorporate the 13, and then 13, we look left. Do we need to move it left? No, because 10 is less than 13. That's good. So 13 doesn't need to move. So now we say that part is sorted, restores that condition that the left subarray needs to be sorted. We incorporate the 5, and then this is how it works. This is a good example of how the shifting works, because you just do it one step at a time. You incorporate the 5, and you look left. 13 is not less than 5. That means 13 should not be before 5, so you swap them. We look left again. 10 is not less than 5. That means 10 should be the right of 5, so we swap them. One last time, I think I skipped a step in my illustration here, but we see that 8 is not less than 5, so we should swap them. Or I should be saying that we see that 5 is less than 13. Um, so we swap it. 5 is less than 10, so we swap it. 5 is less than 8, so we swap it. That's the condition you actually want to use for insertion sort. And that's important to keep stability, as I'll explain. Sorry about that. You want to say that is your current item less than the other item? Yes or no? And if not, you swap it. So that part is sorted. We look at 17. It doesn't need to shift left, so that's good. We incorporate the 2, and I'm gonna not show each individual step because I think at this point you get the picture. But 2, you would need to say 2 is less than 17, so you swap. 2 is less than 13, so you swap. Now 2 is less than 10, you swap left. 2 is less than 8, you swap left. 2 is less than 5, also you swap left. And that's a lot of iterations, but it keeps this part sorted. And again, you incorporate the 0, and it's once again a lot of iterations. It'd be very annoying for me to make these slides if I wanted to show each step at this point. But essentially, you just keep swapping 0 to the left because you say 0 is less than 17, that's true. 0 is less than 13, that's true, so on and so forth. So now you have this sorted subarray. And the last thing that you have to incorporate is this 9. You swap it left a few times, ends up in its right spot. We see that the partition has reached the end. There's no more items in the unsorted subarray on the right side, so we're done. That leaves us with the same sorted array as selection sort did. Now to talk about its stability, I mentioned earlier that it was stable, and I mentioned earlier that the conditioning and the swapping to the left is important as to why it stays stable. So I'll show you why. So basically, we swap things to the left if necessary. So we swap things to the left if and only if the item to the left, or sorry, if and only if your current item is less than the item to the left. That means if your current item is the same as your item to the left, you won't swap it to the left, which then means that it is in the correct order it came with. So you only swap if you need to, so that's the sort does happen. This is a good thing. And when they're tied, we don't do anything. And this is really where the stability happens. So basically, if you have two things that are tied, it's going to come in the original left to right order that it was, which is the definition of stability. So we'll move, eventually we'll do this. So 2A stays the same. We move 3A, doesn't move. 3B is not less than 3A, so it doesn't move. So that means that in our sorted, using insertion sort, our sorted array has 3B after 3A. And then we look at 2B, we move it left of 3B, we move it left of 3A, and 2B doesn't need to go left of 2A because 2 is not less than 2. So in both of these ties, the original left to right order is maintained because we're looking to the left and because we have this as our logic. And since that is the definition of stability, that means that insertion sort is stable, which is a good thing. And I talked earlier about how insertion sort has best and worst cases. So I'm going to talk about both of those. The best case, as I saw, or as I showed in that table earlier, was O of n, while the worst case is O of n squared. Now the worst case, the average case is n squared. You call it an n squared algorithm, but the worst case, the worst kind of input you can give to insertion sort is the slowest n squared there is. That's what we're going to consider as the worst case. So if you think about the earlier example and where I lost my patience and decided to not show each step, when did that occur? Well, basically, that occurred when we had small items at the very end, because that would require a lot of swaps to the left, right? At each iteration, if you had to say, oh, I've got a small item all the way at the end, I got to move it all the way to the beginning. Oh, I've got another really small item at even further end, I got to move it even further to the beginning. So if we extend that and say, then what is the worst possible input you could give insertion sort to make it do the most number of swaps? That would be a reverse sorted order array. That's our worst case, because that you want to work it out yourself. You could try like 9, 8, 7, 6, 5, 4, 3, 2, 1. It's a lot of swaps. So that's the worst possible case to do insertion sort. Thank goodness I did not choose that as my example to show. And that ties back to the meme from the first slide, if you remember that. So then what would be the best case? Well, for insertion sort, it turns out you just reverse this. An item or an array in already sorted order, um, and it turns out arrays in almost sorted order as well are on the order of O of n, because once again, if you want to walk through it yourself, or you could take my word for it, but these sort of arrays require very, very little swaps. So this is an important thing to know. If your array is almost sorted or sorted, then insertion sort is linear, because all you have to do is just check each item and say that it's already in the right spot and you're done. And you might be thinking, oh, well, obviously if something is already almost sorted, then it should be easy for any sort algorithm to do that. That's not always the case. There are some algorithms that are not good for things that are already sorted, like quicksort. Quicksort's worst case actually comes when things are almost sorted. So you would imagine that quicksort could use insertion sort when it's already or when it's close to sorted, because that's the fastest possible way to do that. So that goes to show how these algorithms can be used together and how there are benefits and drawbacks to each algorithm in the real world. Once again, in case you didn't believe us in lecture when we told you that. So a final overview, looking at the combined tables between these two algorithms, we'll see that insertion sort has a better best case than selection sort and is stable as opposed to selection sort. So just based on these statistics, it seems that insertion sort is always preferable to selection sort. So selection sort is always n squared. Like I said, insertion sort is stable while selection is not. So you might be thinking, why the heck would we ever want to use selection sort at all as opposed to insertion sort? Well, it might depend on the type of data structure you're working with. Think about in arrays. Think back to maybe 142 or 143 when you had to do this. In an array or an array list, which uses an array behind the scenes, when you have to insert something, which is what insertion sort does, when you have to insert something to the left part of an array, what does that do? That has to shift everything to the right of it right one spot. And that actually can be pretty costly. So if you had to do a lot of those insertions where you're moving something in one and you're moving something, you have to swap a lot of things to the right. You have to shift everything over to the right. Insertion sort could be really slow in an array. Whereas selection sort, if you just have to swap two items, you could just say that, hey, temp variable index of this or array of this index is equal to that item, array of the other index is equal to temp. It's very, very simple constant operation. And then something to chew on. Maybe this would be different for a linked list. I don't know. But point is, there are some cases where insertion sort would be slower than selection sort. It kind of depends on how your data is formatted and what structure it's in, a lot of things. But selection sort is not completely useless and not something you should just discard. It's important to know. Both of these are. Yeah, both have a worst case of O of n squared, as I mentioned. And also insertion sort, again, is on the order of O of n when the array is almost sorted or completely sorted. This is really, really good to know because this can be used in tandem with other array or other sorts that don't do so well with almost sorted input, like quicksort. So that's all I got for this video. Hopefully this was helpful in illustrating the differences between these two very similar algorithms and showing you how both can be useful, especially insertion sort in the real world. So yeah, thanks for watching.